Hello out there, and welcome to this introduction. As Jacob said, my name is Morten, and for the next about 45 minutes, I'll be giving you sort of a very high-level fly into Bayesian optimization in the context of physical experiments, and I'll say a bit more about that. As we move along, if you have questions or things you would like me to elaborate on, please feel free to begin typing them into the chat so that we can sort of wrap up everything with some Q&A at towards the end. All right, but let's get into it and what I'm gonna talk about. So my focus is really on solving a deceptively simple problem, which is to find optimal settings for a process or product based on a set of predetermined quality requirements. And this is very easy to say at a high level and very difficult to do in practice. But what I'll be focusing on in this little introduction is that one way of attacking this problem is to use Bayesian optimization. And if you're new to this field, I will be showing you the software tool Brownie B, which is meant as an entry-level software tool for Bayesian optimization. But more on that later. So a little bit of context. Why am I giving this introduction? Well, mainly because here in Denmark, I have implemented Bayesian optimization in the R&D department of about a dozen companies over the last 5 or so years. So I have seen a lot of examples of where this type of method can bring value. And I've also seen a lot of cases where it can't. Or where things might handicap this approach if you're not careful. And I'll be sharing some of that with you today. Just a little bit of context of who my organization is, because this is a very multinational crowd. So my company is called, or the company I work for is called the Danish Technological Institute. We are a research and technology organization in the sense that we own ourselves and we exist to increase the competitiveness of industry by using or implementing technologies as they show up. And we do this mostly focused on the Danish industrial sector, of course, but we collaborate with a lot of companies. So in the center or the business unit where I work, we mainly focus on implementing the green transition in practice. So lots of materials recycling within plastics, textiles, critical raw materials, like rare earth metals and so on. And we typically do this in large consortia of companies like some of the ones that are shown here. And in a lot of these, we have to improve processes and or products using experiments. And that's where tools like Bayesian optimization comes in. So Bayesian optimization is an experimental design method. And so I think for the people who might not be familiar with it, it's good to sort of put it in the context of broad experimental design, why it's a good idea in the first place to use tools such as this. And the thing is, as I am a chemist by background, and I know from hard-earned experience that optimizing processes and finding the optimal settings for something is not something that's easy to do. We can't just sit down at a desk and think about all the things that we could foreseeably control in a process and from our desk figure out what to set these at in order to achieve a certain yield of a chemical process or a certain viscosity of our resulting glue or whatever. We have to carry out experiments in the real world to produce information that will allow us to sort of figure out this connection between the things that we can control and the things that we want. And I like to think about experiments in this way and frame it in this way, that the reason we do experiments is that they are essentially measurement systems that we use to produce data. And these points of information or data are useful as building blocks for models of nature. And if we use them in the right way, then these models can be used as maps to sort of guide our way through this complicated process to the goal as fast as possible. Now, a lot of the time in an R&D department, you will also hear people talking about we want to sort of understand our process in order to improve it. And in a lot of R&D departments that I've worked with, this may or may not be true for yours, but when we talk about understanding, typically what people mean when they say they understand a process is that they are able to create graphs like these ones. In the sense that if I can show you a graph that sort of tells you what the quality is going to do if I reduce pH, for instance, or if I change from one enzyme to another, if I can draw this graph reliably from data, then we will say that I understand what pH does to my process, or in this case, to my quality. And all of us are taught to decipher graphs like this from very early on in school. But it's very tempting because we are shown, understanding in this way, in this one-dimensional way. It's also tempting to collect data in a one-dimensional way in order to produce these graphs, right? So the problem with that is that building models of nature one factor at a time, where we just change one thing and keep everything else constant, is extremely ineffective. And as an example here, we might have a process where we could change temperature and we could change, say, the reaction time, and then have quality as the vertical axis here. And in a one factor at a time approach, we would pick a time and then do a temperature series and collect maybe these data. And then the quality is best at this temperature, so we fix our process at this temperature and then change time. And then gather some more data, and then, maybe we ran out of time and the project deadline came up, or the manager became impatient, and we have to deliver this set of settings as the final result. And this way of exploring a process space is extremely ineffective for a variety of reasons. One is that your final result is going to depend upon which thing you changed first and what you did with all the other settings when you made that experiment. So you have very few guarantees that there won't be a better solution hiding somewhere within this playing field that spanned by the settings that you have tried. And if you have more than just two factors, this becomes very difficult to sort of wrap your head around where have I even been and what have I tried and what do I know when we build knowledge one factor at a time. Now, this is not a particularly new problem, and there exists an approach to handling this called design of experiments, which is more than 100 years old. And in design of experiments, what you start out by doing is thinking a lot about what is this playing field that I could collect data from. And then today we use some algorithms to suggest a set of experiments where we would go to collect data, not because we care about these particular data points, but because we need to use these data to draw this map. And then from the map and the understanding that that brings, we would make a suggestion of this is probably where the best solution is. And even though design of experiments in the classical sense is not a focus of today, it is, I think it's fair to say, a very successful method and has lots of examples of this working well. The issue from a practical standpoint from a lot of industry is that the number of experiments you have to run in order to build a reliable map when you have a complicated process, say 10 or 15 or 20 factors, the number of data points you have to collect to draw this map is very big. And the budgets don't necessarily come, match to the difficulty of the problem. And in a lot of cases in industry, you don't care about the map if there's no solution, in the sense that if you don't get the good enough performance, then the map has no value. This is where Bayesian optimization comes in. So in Bayesian optimization, we still have to think about this playing field. Where could we foreseeably collect data? But instead of collecting a lot of data to be able to draw all of the map at once, what we do is we collect slightly fewer data points, or a lot fewer data points in some cases, draw a map or collect data there, and then draw a map that we know at the beginning is going to be very uncertain. And then we use a different type of algorithm to suggest somewhere to go and create one new data point based on the knowledge that we got from the first ones. So in this case, the more yellow the color, you could say, the greater the probability that we will see an improvement at that location, given what we know at that state. So we collect the data point here in the corner, get this result, redraw the map, ask the algorithm for another suggestion. So now it wants us to go and check in this corner. We go there, collect data point, update the map, ask for another suggestion, collect the data point, and then in this case, maybe the map stops changing very much, or we get a result that we're satisfied with and we stop. And these two things look very similar when there's only two factors. So two things we can change. But the advantage of Bayesian optimization here is that the number of experiments it takes to reach a solution when it exists, it doesn't scale anywhere near as badly with the number of factors as classical design of experiments does. And this is sort of the main argument for using this approach to solve problems in an industrial setting. You should use Bayesian optimization when you really only care about finding a solution as fast as possible. And especially if, having the map has no value to you if the solution is not good enough. But I think both of these should be part of your toolbox as experimenters. But as we will see, Bayesian optimization might actually be easier to begin using if what you're doing right now is changing things one factor at a time. The learning curve might not be as steep as with classical DOE. So to show you the workflow, in Bayesian optimization, we have to sort of start out thinking about what we want to achieve, and then how we will measure quality in the sense of how will we measure whether we're getting closer to this goal. We have to think about the factors that we can change and what the limits of those are before we begin experimenting. Then we will start out, as I said, to collecting a small data set. Then some scary math will take care of figuring out a suggestion for the next experiment. But the scary math will produce a set of suggestions for what to put all your factors to. Then we will carry out that experiment and add the result of that experiment to our small data set, and then run around this loop. But let me show you what that looks like on a much more complicated problem than just a two-factor problem in 1 minute and 51 seconds. So imagine you want to improve the PCR reaction, so to multiply DNA, say for a corona test. A PCR reaction here is a quite complicated set of kit. So we have to define a quality metric here. And this quality metric is going to be the effective yield of our process. So this produces a little bit of DNA at a certain purity, and the effective yield is going to be our quality metric. Next, we're going to consider what factors we can change. And as I said, this is a complicated machine. So in this case, there are 12 factors that we can optimize, with each with a higher and lower limit. And the starting conditions that we're given, they give a very, very low yield compared to the goal that we have. So here's how Bayesian optimization would proceed in this case with the small data set. So we're going to collect information at, in this case, 14 initial runs where none of the settings are identical across all of them. So we're just spreading out data points across this huge space. And these experiments will give us some initial data. So a little bit of information on what the quality is at these very different settings. And this will be enough to suggest a new experiment for us, because the algorithm will take this data set, suggest one new data point, we'll carry that out, add it to the data set, and repeat. So this is what the first one looks like. And then iteratively, we will just add more and more and more information until, in this case, after 25 runs, we reach a yield of above 500. So we could in principle stop here, but maybe we should also look at what each of these settings do at this stage. So right now, the expected best setting is at sort of the upper limit of 3 of our factors. And it turns out in this case, we can expand the space further in that direction. So we'll do that and see where we can go from there. So sticking to the same approach, drawing one experiment at a time, after 35 runs, we get to a yield that is almost twice our initial goal. And I want to show you that addressing this problem with the classical design of experiments approach is not very appealing, because in the DOE approach, with this many factors, 12, we would start out trying to reduce the complexity of the problem, maybe with something like a definitive screening design, which would take maybe 30 runs. And then we might actually discover that all of these factors are important for a complicated process like this. So instead, we would then continue to sort of build the full map by augmenting, as it's called technically, to a full surface. And that would take at least another 70 experiments if your data quality is really high. So that means with classical DOE, we would have to run 100 experiments before we have any idea whether there's a solution to be found anywhere in the space, in the ideal case. But to make matters worse, for classical DOE, it's because of the way the math works in that approach, you tend to carry out experiments in the corners. And for many processes that are really complicated, the corners are the last place you want to go and look. The extremes of the process are rarely where the solution is going to be. And this is why in practice, when people who work with complicated processes, they often struggle to implement classical DOE in their R&D department because it takes a lot of work to build these kinds of models. But that said, I should stress that it is the full method that is effective. And you can certainly handicap the Bayesian optimization approach if you don't think about your goals and your quality metrics and if you feed it bad data and so on. So we'll get back to that. Furthermore, if you are just starting out in this field, you might Google a little bit and you'll find a bunch of open source Python packages that allow you to do Bayesian optimization, but you have to figure out you have to make a lot of choices that are complicated for new users, such as what is the size of small? Like how many data points should you start out collecting before you begin running the optimization loop? What does an optimal next experiment mean? How should I take the three things we typically measure on our paint and turn it into a minimization problem for this Python package to work with it, because it says it can only minimize? How many factors can I realistically attempt to optimize in together? Is it 5 or is it 10 or is it 200? What is the limit here? And how do I figure out when to stop? And should I replicate at some point and so on? All of these choices, I think, actually make picking up Bayesian optimization a little bit difficult if you are, walking down the approach of finding a Python package. Furthermore, if your colleagues are like my colleagues and like I was before I met DOE, you will probably have colleagues who are very certain that one factor at a time is a good way of conducting experiments. Because in most scientific education, you are not taught statistical experimental design, and you're certainly not taught Bayesian optimization because it's a much newer approach. So most scientists and a PhD in chemistry here, when I left university, I lived up here as well, live at the top of Mount one factor at a time, where they're very confident that what they're doing is the right way of experimenting. And if you ask them to begin working with Bayesian optimization, then maybe it's a little bit difficult for them to get anything working in Python. And they might not be very in touch with, the uncertainty of their measurements and the data quality. It might be that they don't even measure the thing that they're trying to optimize. This is quite prevalent in, for instance, if you're working with food, sort of measuring things that correlate strongly with human taste perception is notoriously difficult, for instance. And if you try to push DOE on them, they might just not care about having a model for the system. They just want to find a solution and stop working on it and move on to the next thing. So when I go out in R&D departments and teach these tools, I quite frequently, drag people down into and through the valley of despair, as I call it down here, where people have sort of learned just enough to know what they don't know, and have to sort of drag them up this hill towards enlightenment again. And I will argue that Bayesian optimization is an approach where it's a lot easier to get people through the valley of despair if you can sort of lean into this iterative experimentation where you don't have to learn lots of math up front and present things in a friendly, simple user interface. Because the last thing that a lab technician wants is like Excel on steroids or something. And this is where Brownie B comes into the picture. So as I said initially, Brownie B has been built as an entry-level tool for Bayesian optimization. It's a browser-based UI that we have built together with Novo Nordisk and the Alexandra Institute, which is another Danish RTO. And I'll be demoing that in just a sec. I should say, for those of you among the crowd who are still students, we have made this tool free for students, and at the end I'll show you how to get a hold of that. And if you're into all the Python stuff, I should say that the open source, the backend is open source, and there'll also be a link to that at the end. But let me just change what I'm sharing here and jump into Brownie B itself. Here we go. So if you go to browniebee.io, you will find me again. And if you register up here, it just requires your email, no credit card information or anything. You can try out the software for free for 30 days. And I'm just going to log in and to show you what you're going to be met with when you get in here. So this is where my experiments are sort of stored. And for this webinar, I will create a new project, which will appear here at the bottom. And let's set up an experiment. Let's say that we want to work with cake recipes, for instance, and we want some flour in our cake, obviously. Let's say that we think we might need between 150 and 250 grams if we're making brownie, for instance. We might want to add butter and in some amount. We might want to use eggs, and since it's a pain to sort of pick, half fractions of an egg, we're just going to pick discrete. So we will only be told to use, whole numbers of eggs. And maybe we also want to add a color to this cake. So a category here. If you have, a 9-year-old like I do, you might be popular if you add, fancy colors to the cake. So I'm going to add a couple of categories here and set it up here. So you might have noticed as I did this that Brownie B has started suggesting a bunch of initial experiments up here. So these are these few data points that the algorithm is going to need before there is any information to work with. So the more factors you add here, at some point it'll begin adding more than 5 initial data points, but that will sort of scale with the complexity of the system. But let's say that I'm ready to start experimenting here. So I'll transfer my data points down to the table here. And then I would go out and run experiment number 1, and I would want to score the quality of that result. And to help people sort of build the right intuition about this, Brownie B expects you to input a number for quality here. That is, you should simply understand as a number of stars. So if this produced a cake that was really horrible, we will give it a low score. Whereas if we, produce a better result, we will give it a higher score and so on. And normally you would build this directly from something that you measure. And I'll come back to that in sort of the second part of this talk. But you would now sort of build up these initial experiments. And once you fill out the 5 data points in here, Brownie B will begin using your data. Now we'll just load a different experiment to show you what that looks like. So this is just a different coding of another system, but here we have a bunch of results. What has happened now is that Brownie B has begun to use these data points. Maybe I'll actually pick this one because it's simpler to look at. So at this stage, Brownie B has now provides a solution for the next experiment to go and do. And this suggestion is now built on the information we have down here. The initial data points that it suggests are just spread out across the space, but now we are actually building the suggestion upon the information we have. And Brownie B also provides information on, if I were to stop right now, what settings should I report to my project manager as the suggestion for the thing to use? So in this case, with the information we have at the moment, it looks like the best concentration for magnesium would be 6, for potassium 14, and DDT about 1.35 or so. And at those settings, we can expect to see a quality of somewhere between 4.5 and 5. So this figure here is just a histogram of the quality that we expect, again, based on the data down here. And yeah, furthermore, right now, Brownie Bee just shows one next suggestion. I can ask for more than one at a time. But we'll come back to in a moment why, by default, in active learning, you should ask for one experiment at a time, and the advantages and disadvantages of that. But that's really all there is to it. This is the workflow that you would use in terms of using Brownie Bee. So that's simple enough. But let me just jump back into the presentation here and show a little bit about what actually happens under the hood, because I think that's useful to understand in order to use a tool like this. So in Bayesian optimization, the way that we get an optimal next experiment is by using a Gaussian process. That is a technical name for the model landscape that we're using, and an acquisition function. And we'll come back to that. But I want you to imagine that you have been given this small data set. There's a single factor that is changing along the x-axis. And again, we have quality along the vertical axis here. So the question is, how would you explain these data? What trend do you think is realistic to explain the data that you have here? Maybe you might imagine something like this, or you might imagine that the landscape looks like this, or like this, or something fourth. And essentially, it's important that you are probably not picturing something that looks like this, a jagged landscape. I don't know any physical process where, as a function of pH, your quality or anything looks like this graph. They generally tend, in physical systems, things tend to change gradually and slowly. And a Gaussian process sort of has that built in from the beginning, because you can think of it basically as an average of all the smooth lines that you could draw through the data. So instead of sampling them like this, maybe if you went down to the nearest pedestrian street and asked 1,000 people to draw a smooth trend that could explain these data, you might end up with something like this. And it's a lot easier to just show you the average line here and sort of an interval for how different people are drawing the lines, if you were. So basically to represent the uncertainty about what we know at any given point. Now, the acquisition function uses this model and the uncertainty in answering the question, where would it make most sense to create a new data point in order to reach a certain goal? And note that we have the same x-axis here. So this is basically how much would I like to try each of the settings that I could create a new data point at. And right now it's saying that we should go to this location, so this value, and create a data point here. So we do that, and we get this data point. And now we will go back down to the pedestrian street and ask for another 1,000 smooth lines, and the average will look like this. We can again ask for a new experiment. We'll be told to go here, and we'll gather a new data point. And then we will rebuild a model with this additional information. And the job of good acquisition functions is to sort of also balance whether we use the landscape when we get close to our goal or explore for new solutions. And in this case, we have seen a data point that is quite close to our goal. And since we assume that the landscape will be smooth, then it's natural to assume that there could be the option of reaching our goal close to the data point we just collected. So here we actually asked by the algorithm to go just to the right of the previous experiment, and we get almost the same result. And this means that this data point contains a lot of information about sort of the noise of the system. Again, because the landscape has to be smooth, it can change relatively steeply, but it has to be smooth to a relatively large degree. So in this case, we have probably found one local optimum here at least, because down here and down here, the quality is low, and in here, the quality is high. And if our assumption of a smoothly changing landscape is true, that means that the underlying landscape has to peak somewhere in this region here and then go down again on either side. But it also means that there could be an even better solution hiding out here in the region we haven't explored yet, where the uncertainty is still very big because we have no data there. And in this case, the acquisition function is going to go out there and have a look, so to speak. And in this case, we get a relatively boring result, but nonetheless, we will just repeat and then get a data point above the goal here. And now I'm just going to show you sort of the underlying relatively unrealistic function that this data is sampled from. But if you continued at this stage, you might actually be asked to run a next experiment here or here, because this is some of the regions where we haven't got any information at this stage yet. And obviously this is, an unrealistic one-dimensional system, but the point is just to sort of give you a visual idea of what is actually going on inside the algorithm here. Because this approach works just as fine when you have 2 or 5 or 10 factors. It's the same underlying philosophy that is guiding our experimentation. All right. So I will spend the last 10 or so minutes to give you a little bit of an overview of what has to be in place for Bayesian optimization to work in practice and common pitfalls that you should try to avoid. So no matter whether you are a fan of Bayesian optimization or classical DOE, they require that you think a little bit more upfront. You can't just run off into the lab and begin experimenting, because that will go very horribly. So let's dive a little bit into the things you have to think about here. And the first is having a clearly defined goal. I'm still surprised at how many organizations do not really spend enough time defining what it is they're trying to achieve. And so they commit what you could call errors of the third kind, which is when a specialist goes off into the lab for 3 months and then comes back with a really well-documented answer that is correct, but it answers a question that is different from the one that the project manager thought that they were asking. And Brownie B is focused on sort of nudging the user to improve quality, but there's no machine in this universe that can measure quality, because quality is just an abstract idea. What we can measure are various physical properties of our system or our product. And just saying that we want to improve the yield of a chemical process is not a clear goal, or we want to understand how our process is affected by the various factors is also not a clear goal. So let me give you an example of a more clear goal. For instance, instead of just improving yield, you might want to specify that we're talking about this specific process step where the yield is about 70 at the moment, 70%, but we need to get this to at least 85% by the end of, this was meant to be this year, but yeah, at some time point in the future. And when we say the yield, what we actually mean is the specific number we arrive at when we follow a specific protocol with a specific piece of equipment. And by the way, the total cost of this product can't increase by more than 2%. And the overall budget cap is, say, $100,000. And that might influence how many experiments you can run and so on. Another example might be that you are tasked with finding a better glue for joining 2 materials. But what does that mean in practice? Well, it could be that you have 5 alternatives that you are looking at, and you're only really going to replace the glue if at least one of them is 20% stronger than the present one when we join these 2 materials together under the conditions that are present where we join them together. And when we say the strength of the glue, what we really mean is, again, a very specific test on specific types of samples on a specific machine, and we have a certain amount of resources available. The next part or pitfall that I want to talk about is the measurements of these quality attributes, because Bayesian optimization is no different from any other algorithmic technique that if you feed it bad data, it's going to give you bad suggestions. And I like to illustrate this with the Battleships board game, because Battleships has really horrible data. And in Battleships, if all you get is pass if you hit or fail if you don't. So a data set like this, where we have 14 experiments and all of them were failures in this metric, they don't contain that much information, and they make it difficult to make a good decision on where to try next. But if we change the rules of battleships so that instead of just getting a pass or fail, we're going to get information about roughly how far we were from the target. And if we draw this into our system here, with, at a radius of the distance we were from the little ship we're trying to hit, it becomes a lot easier to sort of figure out where should I probably run my next experiment, even though none of my initial data points were on target. And then we can hit, the target on the other side. And you can, go down the road of figuring out just how much information there is in judgment data, meaning pass fail, compared to when you have quantitative measurements. I'm not going to go into that here, but unless your budget is extremely small, it's nearly always worth it to invest in having a quantitative measure of the thing you're trying to improve. And if nothing else, just because building a consistent method and using instruments will allow you to bring down the noise of the data, which again helps more than almost anything else, is just to get the noise of your data points down. And in Bayesian optimization especially, we put the users in the position of having to define a quality score, this 0 to 5-star number. And that's really to nudge the users to have this discussion before they go into the lab. Because in a lot of industrial settings, what we care about is just finding somewhere where the quality is above whatever the customer will pay for. And it has to be reliably above, in the sense that, the customer is not going to be happy that the glue holds on average if 25% of the time it fails, right? They care about a lower quantile of performance, and that's really what they're paying for. But they're not giving you extra money to overperform either. So when you're optimizing in an industrial setting and improving some quality metric, you just need to find any setting in here where the lower limit on quality is above what's being asked for, and then stop as fast as possible. So there are many ways of setting up quality scales, but I'll just give you a concrete example from one of the companies that I've worked with. EA Carpets, they make carpets as their name suggests. And in this case, we were trying to sort of increase the speed of a production line, but the main thing that was failing was the gluing strength. And they have an idea of how strong the top and bottom have to be of a carpet have to be joined together. Because if this adhesion is too strong, that you can't roll up the carpet because it becomes too stiff. And obviously, if the adhesion is too low, then the carpet falls apart and the customers will also not be happy. And then somewhere in between is the sweet spot. And in this case, you could use a relatively simple, quality metric of 5 stars when you are right on target. And then as you move away, you deduct a little bit from the quality proportional to the square of this deviation on whatever the scale is. So you don't really punish having small deviations from your target, but as you get to these catastrophic points, quality really goes down. And there are many ways to sort of bake in several things into a quality metric. The most important part is really just that you should be able to distinguish whether you prefer this data point and the settings it associated with it, or this data point. Which one do you prefer and by how much? As long as you can do that reliably, then exactly how you set up this math is not very important in practice. All right. The last pitfall I'll talk about is choosing factors and leaning on domain knowledge. So here's the quote that I love the most from the whole statistical experimental design field, which is attributed to Doug Montgomery. And he says that you should never let one person design and conduct an experiment alone, particularly if that person is a subject matter expert in the field of study. And why is that? I think this is particularly true in organizations where one factor at a time experimentation has been the norm for a long time, whether it's a company or an academic group, I should say. Because imagine that we have a process where this is the present settings, and you, as a new employee, are thinking, maybe this could be improved if we change the temperature or the time or both. But there's this experienced colleague you have who's been here for 30 years who says, nah, it's not going to work. We have tried changing temperature and we have tried changing time many times. It's not going to improve quality. And this person might even be able to dig up an old piece of paper where there's hand-drawn data points in a plot showing that they changed the temperature and quality actually went down a little bit. And they also changed time and quality didn't improve. So from their point of view, this experienced colleague has data to back up their claim. They think that they have investigated this in a data-driven manner. But if the underlying landscape looks like this is what this person has been missing, and they have actually learned something wrong because they are using a one factor at a time approach. And this is why you should be wary about leaning on domain knowledge and, we know our system, even though our system has 10 factors and we've only ever changed them one at a time. You might think this is an unrealistic example, but if we just return to thinking about cake, if you try to bake a cake at 50 degrees for 1 minute, increasing the temperature to 200 degrees while still putting the cake in the oven for 1 minute is not going to bake it. And if you stay at 50 degrees, increasing the time to 15 minutes is also not going to bake the cake. So if you use one factor at a time experimentation, you are subscribing to a methodology where that will teach you that neither temperature nor time can bake cakes, right? Right, but enough of that. The full method in Bayesian optimization is what is effective. Relying on the algorithm alone will not save you from making mistakes if you don't think about what you're doing up front. And we built BrownieBee to try and make it easy to get started on this journey if you're new. And that's really all there is to it in terms of BrownieBee. It makes it easy to get started with Bayesian optimization. As said, you can try it for free for 30 days. There's some tutorials on the specific steps of the workflow also on the website. And if you use the QR code here, that will take you directly to browniebee.io with the referral link that Jacob has provided here for this seminar. As I said, students can open up 6 months of free access and get that extended if you email support-bb@alexandra.dk. So shoot us an email from a university domain, and we will sort of keep opening 6 months of trial for you. And then you should also feel free to contact me if you have any questions about BrownieBee. And finally, as I said, the backend is open source, so you can look at the internal workings that run in Python that live underneath the hood in BrownieBee. But I think I'll end it there and open up the floor for any questions that the crowd may have.
Wonderful. Yeah, thanks, Morten. I'm first of all, a great presentation. I think there's still quite a few things that I learned myself here. I'm quite surprised. We have 120 people here, so this was supposed to be the soft start, with the real thing starting in 15 minutes. But it seems that the two people that last year said, "Can we please have an introduction to Bayesian optimization?" wasn't maybe just two people. It seems to be a little bit more than that. So. That means also we have some questions here, so I'm gonna just read them out via the Zoom system. So the first one is, how many initial data points do I need to start with Bayesian optimization?
Yeah. So it's something where there's no right answer yet. It's something that's still a bit of an open question, but I think empirically what we are starting to see from academic papers and simulations that I'm running is that as a rule of thumb, you need something like the order of the number of factors you have, maybe slightly more. So let's say if you have 4 factors that you're going to vary, you should run 5 or more initial data points. You can sort of think of the extreme. If you run a single data point in any space, you have no information about where to go next. So the number must clearly be bigger than 1. But in order to save work compared to DOE, you're also not going to run 5 times your number of factors, because then you might as well do a classical design of experiments plan Um, so right now, Brownie B is configured to do your number of factors plus one. Something on in that order of magnitude, maybe slightly more, is probably a good place to start for most systems.
Great. Okay. Thanks for that. The next one is, does Bayesian optimization only work if I choose one experiment at a time?
Hmm. Um, no, you can definitely do more than one at a time. And I think the easiest, it's probably easier to show this if I go back to Brownie B here. Share. So I mentioned this that it's most efficient to run Bayesian optimization one experiment at a time because the typical algorithm, this acquisition function that I showed you for choosing the next experiment, there's really only one place where the probability of reaching your goal is greatest, and that's the settings that Brownie B will suggest. But at the same time, it may be that you're running experiments in an incubator and each incubation takes 3 weeks, but you have space for six in your incubator. So it's a waste of time to only run one incubator at a time. And in that case, you would increase the number of suggestions here. And if all goes well, the first suggestion should not be changed by asking for more. Yeah. So the first suggestion is the same. But what happens here is then what do we then do after the first one? Because there's only one best suggestion. What Brownie B does is that it places, you could say, maximally exploring data point as the next one. So this is the point that is furthest away from anything you have tried before in your space. So basically, it looks at where are all these data points located and how can I get as far away from that as possible in my space, including this suggestion here. So that's experiment number 2. And experiment number 3 is then the same thing. Try to get as far away from any data as possible, but keeping these 2 suggestions in mind, and so forth. And this you can continue doing up to 10 in Brownie B. If you use the backend or another Python package, you can do as many as you want. But at some point, you sort of get to the stage where are you really saving work compared to DOE? And as you get closer and closer to an optimum, this way of choosing experiments will place data anywhere but your optimum. But in a complicated system, by all means, run more than one experiment at a time if it's practical for you to do so, and practical and cheap, I would say.
Okay, nice. Quite a few more questions have come in, so I'm gonna try to batch them. And one is sent, a few of them essentially asking, when does Bayesian optimization not work well? So are there
Mhm.
indicators of potential trouble? They suggest maybe there's something like poor signal to noise. Maybe
Yeah,
comment on that.
yeah. Like any data-driven technique is going to fail miserably if you provide it with really poor data. And Bayesian optimization is no magic wand in that regard either. Um, So if your signal to noise is really, really low, then you're going to need a lot of data points to even to average out the noise, right? So what I always recommend before you go out and do the first experiments is to run some standard settings or your best first guess and run it several times if it's a system that is new to you to figure out like how much noise is there when I run this process again. Because let's say on a scale of 0 to 5 stars, if you do the same thing twice and some of the time it gives 0 stars and the next times it gives 2 stars, then you're really going to struggle to make any progress. So that is a really bad case for any data-driven technique, including Bayesian optimization. Bayesian optimization also doesn't really help you if you have lots of categories. So by categories, I mean things like red, green, blue, yellow, pink, where there's no order to these things that you can sort of establish. So let's say you have 50 different enzymes and you have no way of putting them into a factor. That is not something Bayesian optimization is good for. Bayesian optimization is good for helping you when the thing you can change is sort of a continuous thing like temperature or time or pH or concentration or anything that can sort of vary smoothly. Uh, or that would affect quality in a way where it varies smoothly. That's what Bayesian optimization is really best for. You should use different math if you have sort of a lots of categories with lots of levels. Um, yeah, these are the first things that spring to mind. I could probably come up with more, but I don't know if you also have an opinion on that, Jacob. Jacob.
Um, I do have an opinion. I also have a lot of questions that keep coming in. So I'm gonna prioritize those that are closer to the beginning stage, since that was the intention of the session here. There's
Yeah.
three, four questions that are quite advanced. Morten, you can always answer them in the chat, I think, when you pull up the Q&A window as
Mm.
well. In fact, I think I'm gonna leave them for a discussion section. So we're gonna move into the main talks in 10 minutes, and then after that, we're gonna have a discussion section. I'm just gonna keep those questions, those advanced questions for that.
Yeah.
But I'm going to just move on with one that's related to what you just talked about. So, how does Brownie B specifically deal with categorical variables? You already
Yeah.
explained.
So under the hood, Brownie B just uses what's called one-hot encoding. So categories are just placed on a number axis, and but in a way where the only thing that the algorithm assumes is that sort of if I have three categories and I've tested two of them, then my best guess at what the third is going to do is going to be the average of the other ones. That's really all that we do to handle categories. But we can work with categories in Brownie B. It's just if you mainly have categorical variables, you should probably look at a different sort of optimization approach than Bayesian optimization, I would say, or at least in Brownie B.
Yeah, I think
Mm.
we are gonna use the whole time we have here for some
Mm.
more questions. It's really great that
Mm.
they're all coming through. So the next one is, do we need replicate experiments to be more confident about the experimental regions of
Mm.
higher uncertainties? So there's obviously a
Yeah.
a folded question there, but yeah.
Yeah. I mean, I would say it depends on how well you know your measurement system, right? So just to show this again, if you have extensive experience with measuring whatever property of your product that that you're putting into this quality number, say if you measure the strength of a plastic as you pull it apart, for instance, and you have extensive experience with how variable is this number, then you can relate it directly to this histogram at the end of Brownie B, where this is just this interval here is the average quality plus minus two sigma, two standard deviations of that data that it's inferred from your results. So if you know from experience that this is a relatively realistic amount of noise for this type of measurement, then you can trust your model to this degree. The way that we plot quality here in Brownie B includes measurement uncertainty. So this band really represents, where is new data going to land 95% of the time. And when we don't have a lot of data, these uncertainties are going to be really, really big because we don't know the landscape. So I'm just going to click them off just to show you what that looks like in the beginning when we don't have a lot of data. Um, and it's going to hang a little bit because it calculates six. But we should just to show you that here the uncertainty is going to be really big in the beginning because we don't know, is it the landscape different or what is our data like? So if you know your data source and you know its variability, you can use that information compared to the model here to figure out whether you like to what extent you should trust it. Yeah. So a slightly long answer, but I hope that sort of captures the whole thing that this
Yeah,
question.
if it doesn't, that person may just submit the
Yeah,
question
that.
again. Here's one that came through to the chat, so it's easier if people submit with the Q&A function, but I can also
Mm.
go with the chat here. And it's asking, what about this situation where the design space is modeled in silico first, so maybe some simulations, and this is used as the initial data points? I find that quite an interesting question.
Hmm. Yeah. So I what I get from that question is when you could say your factor limits are, or is this question asking whether sort of about the case of trying to find reasonable factor limits in silico to then inform physical experiments? Is that what you're getting
I
from that
think that's
question?
probably one way actually you could go about it, but I think they're specifically saying, let's say I have 2 weeks of simulation runs, 10 data points. Can I use those to kind of as the initial data points. And the data points that they collect afterwards presumably are real world experiments, but the
Hmm.
initial data points come from a simulation.
Yeah. I mean, how what's mainly going to matter in that case is, how well does the simulation capture the real, like, what's the correlation with the real system? But it's pretty common. I mean, these algorithms that in Bayesian optimization, they are, much more extensively used in the simulation world. There's a reason why Facebook maintains one of the largest active learning open source repositories in Python, and that's because they're using it for, computer simulations. And I should be clear that that process optimizer, the backend here for Brownie B, has been, hard coded and configured for physical systems, because you can say that in computer systems, your landscape can change much more drastically than is what is realistic in physical systems. But these initial data points that are spread across the space, I think that's, if you are going to run an in silico model up front to get a rough idea of where to go, then using space filling and maybe iterative Bayesian optimization in the in silico loop might also be sensible. Depends on the circumstance and so on, but people do use this approach for in silico optimization all the time.
Hey, thanks so much. We have 3 minutes left, but still 10 questions. And I'm trying to use the one that's most helpful here.
Yeah. I'll try and answer the others in text, like afterwards.
Yeah, and we'll take them into the discussion section now as well.
Mhm.
I think I'm gonna choose this one here. Does Bayesian optimization work better for processes approximated by low order polynomials or with more complex processes with multiple local optima? So it's a bit more advanced here, but
Yeah. So this is basically, the question is basically about, like, how much do I have to assume about the shape of the landscape? And I would say that Bayesian optimization is it's much more robust to having complicated shapes of the landscape, including local minima, and it handles, getting out of local minima much better than classical design of experiments. So in classical design of experiments, you have to assume a low order polynomial is a good, approximation of the shape. But that's not the case with Bayesian optimization. You can tolerate, much more drastic changes in quality and narrower optima. So you don't have to make as strong assumptions about the underlying landscape. The main assumption is that things are changing gradually, sometimes steeply, but gradually.
okay, wonderful. I think um, we're gonna take a little 1 minute break here before we start. Um, and the questions are still in the Q&A, so we can just return to them later. But thanks so much, Morten. This was exceptional, and you had a really big audience here, so we're at 130 now. So I'm really keen to see where this goes here. Um, and yeah, so we're gonna take 1 and 2 minute break and probably start just after the full hour. And I see you guys soon.